Hello engineers, in this thermodynamics video I wanted to talk a little bit about units. As you know, thermodynamics is all about energy, moving energy around and transforming it from one form to another. So energy has the units of joules. That's the SI unit for energy. And I want to talk a little bit using physics first principles about what a joule is and how to interpret it. So you might remember from physics, there's the work energy theorem that tells you that work and energy are related and that work is equal to force times distance. And so if I want to think about what a joule is, work has units of joules because it's related to energy. Force, the SI unit for force is going to be a Newton, and the SI unit for distance is a meter. So a joule, 1 joule is equal to 1 Newton moved over 1 meter, 1 Newton times 1 meter. I could break this down even further. I could think about the second law, Newton's second law. Force is equal to mass times acceleration. It tells me what a Newton is. So a Newton is equal to a mass, that's a kilogram, times acceleration. Acceleration is meters per second squared. And so a joule, 1 joule, is going to be equal to 1 kilogram times 1 meter per second squared times a meter, right? So we have the force times the distance. And so this is the force and that's the distance. We can combine these units. So it's a kilogram meter squared per second squared. I want to show you how this kind of thinking can be useful. A lot of times, or maybe sometimes this summer, I'm playing with my son, and he has a water gun that has this big reservoir up top, and then it can spray water out. And so you pump up the reservoir, and you're adding energy to the system in the form of pressure. So this has some pressure inside of it, and then it converts that into kinetic energy as it sprays it out. And so we know that the unit for pressure, the SI unit for pressure, is a Pascal. And pressure is equal to force divided by area. That's the definition of pressure. And so if I think about a Pascal, the units of force is newtons, and the units of area is meters squared. And so Pascal is a Newton per meter squared. That's not very much force. If I think about a meter squared, it's like the size of a coffee table. And if I think about what a Newton is, a Newton's like about the same as a quarter pound, maybe like a fast food hamburger patty. And so the weight of one hamburger patty spread out over a whole coffee table would be a Pascal. Atmospheric pressure is approximately equal to about 100,000 pascals. So we'll often see pressures reported in kilopascals in thermodynamics applications, because 1 Pascal is not very much pressure. But going back to how we convert this to energy, this pressure into energy, they have different units, right? The units of pressure, do we have energy? We said the units of energy were newtons times meters, and the units of pressure are newtons per meter squared. So we might want to ask ourselves, what variable would we multiply pressure by to get the energy in that tank? And so if I look at this, I can see if I'm trying to get to Newton meters, I need to multiply this by meters cubed. And the variable that has units of meters cubed is volume. So pressure times volume has units of energy. That's helpful. So the energy in this tank is equal to the pressure times the volume. And now they have the same units. This is really helpful because I don't have to know the formulas. I can kind of figure them out by thinking through just the units. I'm going to show you one more example. This one's related to power. Power is another common unit, and the SI unit for power is going to be watts. And I use this symbol to represent power, E dot, or I also might use, when I'm talking about the work, I might use W dot. Both of these have this dot in it. That just tells you it's a rate. power is a rate of energy. And so a watt is equal to a joule per second. It's a rate of energy. We might also be talking about other things that are rates. I might talk about the volumetric flow rate, V dot, which is going to be equal to the volume per change in time. The power is the rate of energy. If I'm thinking about electric power, the electrical work from a circuit is going to be equal to the voltage times the current. And so if I'm looking at a battery, similar to my super soaker, I might have a battery that I'm trying to think about how much energy is in that battery. If I want to know how much energy is in that battery, then I need to go from power to energy. The energy is equal to the voltage times the current times some unit of time. And this is really helpful. So when I look at the battery, batteries usually have a voltage. It might be like a 1.5 volt battery or a 12 volt battery or a 48 volt battery. That's analogous to the pressure in my super soaker. And then it has this term, which is about the side analogous to the volume. It's the current times time. And many times the batteries have an amp hour or milliamp hour rating that will tell me how much energy is stored. So I can calculate how much energy is stored in that battery in joules, and I can understand how I can use that energy. So I just wanted to show that quick video showing how I think through units. When I'm working through thermodynamics problems, I always try to incorporate units on everything I do. It's really, really helpful. And you can write these physics formulas down, these first principle physics formulas like pressure is force over area, work equals force times distance, force equals mass times acceleration, and you can get some really useful stuff out of those. So I hope that's helpful to you as you're solving problems in thermo.